On this next section, page 2, we're going to talk about linear approximation, and this is kind of what the marginal cost is looking at. So linear approximation is this idea where when you have a curve, if you look in a small area around the curve, basically the curve is linear in this small area. So around this particular point at 1500, essentially this is a straight line. It is not exactly a straight line, but it is close to a straight line. And so if you know the value at that point, you can approximate the value at that point by assuming that this function is linear. Now, when you get, and what this is kind of illustrating is you can't go too far, because once you get out here on this curve, if you use this point to approximate the value of the curve, the cost in this case, you're going to be pretty far off. So you don't want to do that. But if you're just going out, because this is a distance of 500 in this case, that's a wide gap. But if you're only going out a few units, then you can estimate this by a linear model as if it was linear. And so the way we do this, if we go back to what the derivative is talking about and what the derivative is representing, so go back to our original formula, f of a plus delta x, and then subtract the original over delta x. So delta x is just, so if 1500 is our a, delta x is just moving out some, it's the change in x. Delta x is the change in x. And yeah, this is essentially a slope formula. So the change in x, slope is change in y over change in x. So this is, we start at this value f of a, and then we move some distance away. So say from right here to maybe right here, or maybe we go out to where the end of this little enclosed area is. So this top part, the numerator here, would give us the change in y. The denominator gives us the change in x. This is just the slope, and we know that the derivative is representing the slope. So now if we rearrange this formula, we can get, so this part is the new y value, the f of a plus delta x. That's the new y value. So if we rearrange this formula and solve for this term, so we'll cross multiply, and then we'll bring the f of a over. So essentially we're solving for f of a plus delta x. So that would be f of a plus f prime of a times delta x. And so all we've done is we rearranged the slope formula so that we now have and we can get an approximation for a new y value that is a little bit further along than where we started. And if you look at this formula, this is a linear function. So here is our slope, and here is our y-intercept, if you like. So because the y-intercept is basically a starting value, and if we're starting at 1500, that would be the y value where we start. Derivative is a slope, and then this is just how many x units are we going to move along from where we start. So with this formula in mind, and you don't necessarily need to memorize the process, I guess, of how we got here, but it does help. Rather than just kind of memorizing formula, I think it helps to kind of see where the formula comes from. And so that's where it comes from. So with that in mind, let's look at this next example. We have E of t is the cost for electricity in operation t hours during the month. So E of 200 is 1845. E prime of 210 is $10.12. Use linear approximation to estimate the monthly cost if the factory is in operation 218.5 hours. So whatever, we don't have the function for the electricity, obviously. And you probably should never assume it's linear. I mean, there's no good reason to assume it's linear. But what we can do is over this distance from 210 to 218.5, we can assume that it's essentially linear. And so basically we need to find these parts of this. So our A is the starting, or well, T in this case. T is the starting point, which is 210. So that's our anchor. That's what we know. And then we want to get to 218.5. So our delta T is going to be 218.5 minus 210. That is how much T is changing. So that is 8.5. We know that E of, or we're trying to find E of 218.5. And so now A is the starting point for T 210. The delta T is 8.5. So if we have T plus delta T, that gives us the 218.5 that we want. So this would be, going by this formula, E of 210 plus E prime of 210 times delta T, which would be 8.5. So now it's just a matter of plugging in. So we have 18.1845 plus 1012 times 8.5, and then that gives us 1931.02. And so that's the approximate cost of the electricity usage. So all we did, it's the cost is changing at a rate of 1012 per unit at that point. Now, if we assume that's constant and move out 8.5 units, then that is the new cost. So yeah, so just kind of work through this example. Maybe watch this again and kind of get used to using this. I mean, it's just a linear function. You just got to get used to starting at a non-zero amount, but it's essentially the same when you graph linear equations back in algebra and pre-calculus. What would you do? You would find a point, and usually it's a y-intercept, but you could find any point, and then based on what the slope is, you would move up and over or down and over whatever units that represents, and then you get another point. That is all we're doing here. We're moving left this many and up this many in this case. Okay, so all right, so we'll stop this one here and we'll continue the next topic on the next video.